In this lecture, I will deal with stress analysis by X-rays. X-rays provide a very elegant method of stress measurement in a material. Whenever there is a homogeneous elastic deformation in a material, we find that when a particular set of planes within a grain in that material are properly arranged for taking a diffraction pattern, there is a change in the interplanar distances in that set of planes from the value in the unstressed body. Now, this change in the value of the interplanar distance will give us a measure of the stress that has been put on the material. Now, normally in the X-ray method, we do not measure stress directly. We measure the strain, and then from the strain we calculate the stress. Now, before I get into the techniques of stress measurement by X-rays, it will be better to deal with the fundamentals a little bit. Say for example, if we have uniaxial stress as shown over here, say this is a cylindrical rod of diameter d and length L. Say for example, we have a force F acting in these directions as shown. In that case, the stress will be equal to F by A. A is the area of cross section of the rod. Then strain in the y direction, this is the y direction, strain in the y direction will be equal to delta L by L, which is nothing but the final length minus the initial length divided by the initial length. So, from this strain we can calculate sigma y as E epsilon y. E is the Young's modulus. Now, you see, if we want to measure the stress in the y direction, then one of the methods could be that we have some grains within this rod over here, and there are planes lying perpendicular to the direction of F. So, if we have a grain over here with atomic planes lying in this fashion, perpendicular to the direction of F, then what will happen? Due to the tensile stress, the interplanar distance will increase, there will be an expansion in this direction. So, because of the expansion, the interplanar distance will increase, and if we can measure the interplanar distance after applying the force and also can measure the interplanar distance when there is no force on the body, then we can calculate the strain in the y direction. However, the problem is when the rod is under tension as shown over here, we cannot measure the interplanar distance of the planes lying perpendicular to the direction of F, because it will be difficult to put an X-ray equipment over here. So, instead what we do, we try to figure out the variation of the interplanar distance from grains which have atomic planes lying parallel to the side of the rod in this manner, and then if we have a beam of X-rays incident on these planes, then by the back reflection, by measuring the back reflection diffraction pattern, it is possible to figure out what are the values of the interplanar distances. So, in fact, we can measure the strain in this direction, and from that we can find out the strain in this direction and finally calculate the stress in this direction. So, this is exactly what we do. So, we know that epsilon x, the strain in the x direction, will be equal to the strain in the z direction, because it is a cylindrical body which has been under a force along the y direction, and that should be equal to df minus d0 by d0. df is the diameter, the final diameter rather, and d0 is the original diameter of the rod. So, epsilon x will be f equal to epsilon z, and this will turn will be equal to minus nu epsilon y. Nu is the Poisson's ratio of the material which is being tested. Now, so how we measure epsilon y? I have already said the problems of measuring epsilon y directly. So, what we do? We measure the value of epsilon z by finding out the value of the interplanar distance of a series of atomic planes in a grain of the material, by having the X-ray beam falling perpendicularly on those planes, and then subtract d0, the interplanar distance in the unstressed material, divided by d0 again. So, the situation is like this. So, if we have some grains within the material where the atomic planes are more or less parallel to the side of the sample, and if we have a beam of X-rays falling more or less perpendicularly over, it will make an angle, small angle, but it will still be called a normal incidence. And if we can get the diffracted beams like this is the normal to the planes, this is the incident beam, this is the diffracted beams, although it will be making some angle, we can consider it to be a normal incidence of X-rays. So, by having the diffracted beam from this grain, we can figure out how much is the value of the interplanar distance when the material is under load. So, that is the value we call d perpendicular here, and then have the body in the unstressed condition, and from the same place find out what is the value of d0. So, epsilon z will be equal to d perpendicular minus d0 by d0. So, epsilon y, which is related to epsilon x and epsilon z by this equation, can be found out as minus 1 by nu into d perpendicular minus d0 by d0. So, once we get epsilon y, the strain along the y direction, we can find out the value of sigma y, the stress in the y direction, as minus E by nu d perpendicular minus d0 by d0. So, you see that X-rays provide an elegant method of stress analysis by finding out the interplanar distance of a set of atomic planes in a particular grain which is properly arranged within the material, so that we can find out the value of the interplanar distance in the stressed condition and also in the unstressed condition, and knowing these two values, it is possible to figure out the value of epsilon y, and from that you can calculate the value of sigma y. In actual material, the stress condition may be quite complex, may be biaxial or triaxial stress system existing over there. Now, you see, normally the technique that we use is what is known as a back reflection pinhole method, which I will come to later on. So, what essentially we do is, we all know about the arrangement of the specimen and the film and the X-ray machine in case of a back reflection pinhole method. What happens in a back reflection pinhole method is, we have got our specimen here and X-ray beam is allowed to fall on the specimen in this direction. Then we have got the recording film. Now, whatever is recorded on the film is laid out in this portion, and we can see what the recorded recording looks like. The X-ray beam is incident from this side through this pinhole and strikes the sample at this point. So, what normally we do is we smear powder of a known reference material on the surface of the sample and then take a back reflection pinhole pattern from the composite. So, what will happen? We will get the debinding from the specimen as well as we will get the debinding from the reference material, for which the lattice constants and everything are known. Now, provided we know the value of d, the distance between the specimen and the film, just by knowing the d-spacing of the reference material from this recorded debinding for the reference material, we can easily find out what should be the d-spacing for the specimen, by measuring the radius of the debinding. So, by comparison with the reference material for which the lattice constants are known, we can find out from the debinding of the actual specimen what should be the lattice parameter like. So, this will be an accurate measurement of the lattice parameter. So, this is what we do over here. Now, I will go to biaxial and triaxial stresses, which normally we find in case of an actual material. So, in fact, in an actual material, if we inscribe a small cube within the material, the state of stress at a point will be given by these components. Say for example, on each face of the cube inscribed within the material, we will find there will be a normal stress acting perpendicularly to the surface, and there will be two shear stresses given by that, and this will be true for all the faces. Here for example, this is sigma z, here it is sigma y, this is sigma x, and you have got all the shear stresses tau zx, tau zy, tau xz, tau xy, etc., etc. Now, if we consider all the 6 faces, we will see that there will be some of the stresses are equal to some other stresses within the on the surfaces. As a result, the stress at a point within the material can be given by only 6 stresses. So, if we know the values of sigma x, sigma y, sigma z, tau xy, tau yz, tau zx, then the stress at a point will be completely described within the material. Now, if we change the coordinate axis, for example here, there will be a situation when there is no shear stress present on the surfaces and there will be only normal stresses. So, it is possible to change the coordinate axis of this cubic body from x, y, z to some other, so such that there won't be any shear stresses present on the surfaces, only normal stresses. Now, in that case, we say that the normal stresses will be sigma 1, sigma 2 and sigma 3 along the axis 1, 2 and 3. So, under that condition, the state of stress will be given by only 3 principal stresses, sigma 1, sigma 2, sigma 3, and accordingly the principal strains will be say epsilon 1, epsilon 2 and epsilon 3. We can write down the principal strains in terms of the principal stress values as shown here. So, epsilon 1 will be 1 by E, the Young's modulus, sigma 1 minus nu Poisson's ratio, sigma 2 plus sigma 3, epsilon 2 will be 1 upon E, sigma 2 minus nu into sigma 1 plus sigma 3, and epsilon 3 will be 1 upon E, sigma 3 minus nu into sigma 1 plus sigma 2. Now, we can talk about what is known as an ellipsoid of strain. Say for example, if there is a homogeneous elastic deformation of a material, then a sphere within a material, sphere element within the material will be turned into an ellipsoid, and the equation for that ellipsoid of strain is epsilon equal to A1 square epsilon 1 plus A2 square epsilon 2 plus A3 square epsilon 3. So, this epsilon is any strain in any specified direction, and A1, A2 and A3 are the direction cosines of that particular direction with the directions of epsilon 1, epsilon 2 and epsilon 3. Now, if we look at the situation here, so this is a ellipsoid of strain. So, these are the directions of epsilon 1, epsilon 2 and epsilon 3. Say we are considering a direction like this for epsilon, and this is making an angle psi with epsilon 3, and this particular direction here epsilon phi makes an angle phi with epsilon 1. Now, in that case this equation will be valid. So, if we look at the direction of epsilon here, and the value of epsilon will be given by this, and now in terms of the coordinates as we have shown here, the psi and the phi angles, in terms of these coordinates A1, A2 and A3 can be written in this fashion. For example, A1 can be written as sine psi cosine phi, A2 will be equal to sine psi sine phi, and A3 will be equal to cosine psi is equal to root over 1 minus sine square psi. Now, if we put the values of A1, A2, A3 and epsilon 1, epsilon 2, epsilon 3 in equation 1, and also put the value of sigma 3 is equal to 0, as we know that the stress normal to a free surface is 0, then equation 1 becomes epsilon minus epsilon 3 equal to 1 plus nu by E into sigma 1 cosine square phi plus sigma 2 sine square phi, the whole thing multiplied by sine square psi, or equation number 2. This can be derived from the elasticity theorem. Now, our job now is to try to determine what should be the stress along a particular direction as we have shown here. Say for example, along a particular direction, what will be the value of sigma phi. So, this is what we are trying to find out now. Let us suppose that we have a free surface as shown over here, and the angular relationships between x, y, z and the direction 1 for sigma 1, 2 for sigma 2 and 3 for sigma 3 are all shown here. Let us suppose that we want to find out the value of the stress sigma phi lying in this plane and also lying on the surface. So, we have got this direction, which is the direction of sigma phi. Say we want to figure out the value of sigma phi stress in this particular direction, and the direction is specified by the angles phi as well as psi. Now, how to find out the stress in this particular direction, that is what we are going to figure out. Now, just as we saw the equation for a strain ellipsoid, we can write down the equation for a stress ellipsoid in this fashion, where sigma equal to A1 square sigma 1 plus A2 square sigma 2 plus A3 square sigma 3. A1, A2 and A3, just as before, are the direction cosines of the direction of sigma with respect to the directions of sigma 1, sigma 2 and sigma 3. So, this is our equation 3. Now, the stress sigma phi parallel to the surface at phi degrees from the axis number 1, that means this one over here, is sigma phi equal to sigma 1 cosine square phi plus sigma 2 sine square phi. This is our equation 4. Now, if we substitute this in equation 2, then we find sigma phi is equal to epsilon minus epsilon 3 into E divided by 1 plus nu, the whole thing multiplied by 1 upon sine square psi. This is our equation 5. Now, say for example, if we take d0 as the spacing of atomic planes in a suitable grain in the unstressed condition, and d perpendicular is the spacing in the stressed metal perpendicular to the surface, and d psi the spacing in the direction specified by psi phi, then we can write down this equation as epsilon minus epsilon 3 will be equal to d psi minus d0 by d0. This is the value of epsilon, minus epsilon 3 can be written as d perpendicular minus d0 by d0, that is equal to d psi minus d perpendicular by d0. So, essentially what we are doing here, if this is the free surface, if this is the free surface, and if we have the X-rays incident on the surface in a perpendicular fashion, and if from a suitable grain with the atomic planes we can measure the interplanar distance, then that will be d perpendicular. Now, if we do the same thing in the material, when the material is in the unstressed condition, then it will be d0, and if again we allow the X-ray beam to be incident on the surface in this direction as shown over here, then that will give us the value of d psi, the spacing of the atomic planes in that particular direction specified by psi and phi. So, I will repeat, in that case what will happen, the epsilon will be, the epsilon here is a strain corresponding to this condition defined by psi and phi. So, this epsilon here will be equal to d psi minus d0 by d0, and epsilon 3 will be equal to d perpendicular minus d0 by d0. So, after subtraction it becomes d psi minus d perpendicular by d0. This is our equation 6. Now, if we combine the equations 4, 5 and 6, then we get sigma phi equal to E divided by 1 plus nu sine square psi, the whole thing multiplied by d psi minus d perpendicular by d 0. This is our equation 7. Now, this d 0 in the denominator can be replaced by d perpendicular with very little error. So, this equation 7 can then be rewritten as sigma phi is equal to E upon 1 plus nu sine square psi, the whole thing multiplied by d psi minus d perpendicular divided by d perpendicular. This is our equation 8. Now, this is a basic equation. This equation 8 is the one by using which we can calculate the stress in any chosen direction from the plane spacings determined from 2 back reflection pinhole photographs, as I have already mentioned. And what are those? The one made at normal incidence, the one made with normal incidence perpendicular to the surface, which will give us the value of d perpendicular. The other with incident beam inclined at an angle psi to the specimen surface. So, what we can do? We can make 2 back reflection pinhole photographs. One by allowing the X-ray beam to fall on the surface in a direction perpendicular to it, and that will give us the value of d perpendicular, and again a second back reflection pinhole X-ray exposure in which the X-rays are incident on the surface at this particular angle psi, and that will give us the value of d psi. Now, putting the values of d psi and d perpendicular over here, it is possible to figure out what will be the value of sigma phi, because psi is a known value. In most of the cases we keep it at 45 degrees. So, whatever the angle of psi, which is kept 45 degree. So, this value will be known. Nu is the Poisson's ratio, that is also known. E is the elastic modulus, that is also known. So, we can find out the value of the stress in a particular direction phi from this equation simply by having 2 back reflection pinhole photographs. In one case, the photograph, X-ray photograph is made by having the X-ray incident in a normal direction onto the surface, and in the second case by having the X-ray incident at an angle psi to the normal of the surface considered. So, from these 2 values it is possible to figure out what should be the value of sigma phi. Now, the above is the basis of what is known as the double exposure method of stress analysis by the back reflection pinhole method. The figure here illustrates the setup for the double exposure method. Say for example, this is the specimen surface and this is normal to the specimen surface. So, what we do? We take the experimental stressed material and smear on that stressed material powder of a reference material, so that when you do the back reflection pinhole photography, we will have dividings from both the stressed material and the known reference material, for which the lattice constants and other parameters are known. So, in that case what happens is we do 2 exposures. The first one by giving the X-rays, allowing the X-rays to fall normally on this specimen surface in this particular direction. So, the first exposure is by allowing the X-rays to fall on the specimen surface in this direction normally and prepare the pinhole photograph. In the second case, we allow the X-rays to be incident at an angle psi to the normal to the surface as over here. So, X-rays are allowed to fall in a direction at a direction psi to the normal to the specimen surface. This is the film, and on the film whatever we get is shown over here on a magnified scale. So, this is the pinhole through which the X-rays come and go through and falls on the specimen. Now, this particular ring dividing is due to the specimen say, and this particular dividing is from the reference material. Now, if we look at the dividing from the specimen, we will find that it is not perfectly circular. The reason is this: you see, when we do this incidence angle pinhole photography, then say for example, we have got two series of atomic planes. Now, this is one series and this is another series. Now, what happens is the strain in the direction normal to the atomic planes will vary with the angle from the normal direction. So, you see that in this particular case and in this particular case, the strains will not be the same, and in fact we will see that in this particular case here, when we talk about this particular case, the plane normal is given by n1, and in fact this plane normal will not be at an angle phi, but at an angle phi plus alpha 1. Again, on the other hand, when we talk about this series of planes in another grain giving rise to the back reflection pinhole pattern, the normal is n2, and this is making an angle phi minus alpha 2 with the specimen normal. Now, because of this, we are not going to have a perfectly circular Debye ring from the specimen. So, in this case you will find that the measurement of the radius of the Debye ring S1 is not going to be the same as S2. So, normally when we want to measure the Debye ring radius, we measure it from S1, because from this side the value of S is more susceptible to strain. So, this is much more sensitive to stress or strain, and that is the reason why we always measure the Debye ring from the specimen from S1. So, this is what we do. Now, if we go back to Bragg's law, lambda is equal to 2d sin theta. Now, differentiating we get delta d by d is equal to minus cotangent theta delta theta, our equation 9. Now, if d is the specimen to film distance and s is the Debye ring radius, then you can write for the back reflection pinhole method, s is equal to d tan 180 degree minus 2 theta is equal to minus d tan 2 theta. Hence, delta s will be equal to, by differentiating, minus 2d sec square 2 theta delta theta. This is our equation 10. Now, if we combine the equations 9 and 10, then delta s is equal to 2d sec square 2 theta tan theta delta d by d. This is our equation 11. Now, we already know that delta d by d will be equal to d psi minus d perpendicular divided by d perpendicular, and delta s is equal to s psi minus s1. Now, combining these four equations with equation 8, we can write it down as sigma phi will be equal to E multiplied by S psi. S psi means what? S psi means the Debye ring from the specimen during inclined incidence X radiation. So, this is the situation when we are having an inclined incidence photography, that refers to the radius of the dividing there, minus S lambda. What is S lambda? S lambda stands for the dividing from the specimen when there is a normal incidence photography from the material. So, when we have a normal incidence photography, that means X-ray falls on the surface in a normal way and we produce the dividing. So, S perpendicular refers to that, and S high refers to the value of this S1 over here during inclined incidence X-ray photography. Now, if we put K is equal to E by 2D 1 plus nu sec square 2 theta tan theta sin square psi, you see, because all the quantities are fixed. So, if we do that, we can write down sigma psi phi is equal to K multiplied by S psi minus S perpendicular, equation 14. So, this is basically the most important equation in order to find out the stress in a particular direction in a stressed material by doing back reflection pinhole photography in two different ways, one by the normal incidence, another by inclined incidence of X-rays. So, you see that here if we measure the dividing radius S psi. So, in this case, as I already said, the dividing radius is normally shown by measuring the S1, because this side is more susceptible to strain, and that is the reason why S psi is nothing but this value S1, and exact value of S1 can be easily found out with comparison with the line from the reference material for which the lattice parameters are already known. So, we can accurately measure S1 by comparing with SR, and that value is put over here, and S perpendicular is the value of the dividing which is obtained by taking a normal incidence X radiation and measuring the value of dividing radius therefrom. Now, this K is known as the stress factor, and this can be calculated once and for all for a given specimen, a given incident radiation and given specimen to film distance. Once we do it, we can use it over and over. Very often the double exposure method of stress analysis by back reflection pinhole method is not used. Instead, we can have a single exposure method, so to say, which takes much less time than the double exposure method. Now, in the single exposure method, we get rid of the pinhole photograph using the normal incidence of X-rays. So, if this is the specimen surface, in the single exposure method, we do not use the normal exposure, normal incidence of X-rays, but instead we have only one pinhole photograph using the inclined incidence of X-rays. So, in this particular method, it is necessary to measure not only the value of S1, but also the value of S2. Now, if that is the case, then equation 7 can be applied separately for these two cases of S1 and S2. Therefore, we can write sigma phi equal to E divided by 1 plus nu sin square psi plus alpha 1, as we can see here. For S1, the angle from the specimen normal is psi plus alpha 1, then d psi 1, that means the interplanar distance which has been measured from S1 side minus d perpendicular divided by d 0. You know, the equation 7 can be written in this manner for S1. We will see that the d perpendicular will be eliminated, so that you know there is no need of having the normal incidence X-ray method. And sigma phi for the second case for S2 will be E by 1 plus nu sin square psi minus alpha 2, because here the angle from the plane normal is this. So, it will be psi minus alpha 2 multiplied by d psi 2, that means the value of interplanar distance calculated from the S2 side minus d perpendicular by d 0, this is for S2. Now, since alpha 1 alpha 2 these are very small, we can write alpha 1 equal to alpha 2 equal to alpha, and this is will be equal to 90 degree minus theta, the Bragg angle. And if we eliminate d perpendicular from both these equations, then we find the sigma phi can be written as E by 1 plus nu, the whole thing multiplied by 1 upon sin 2 psi sin 2 alpha into d psi 1 minus d psi 2 by d 0. This is our equation 15. Now, if we put k prime equal to E by 1 plus nu multiplied by 1 upon sin 2 psi sin 2 alpha, you know all these things can be calculated and we can find out the value of k prime. We can write sigma psi is equal to k prime multiplied by d psi 1 minus d psi 2 divided by d 0. So, in this method we need to know the value of d 0 in order to find out the value of sigma phi. This is important. That means d 0 is the plane spacing in the unstressed material. Normally, if we know the lattice constants of the material, it is possible to figure out the value of d 0 in any case. So, the advantage of this method is here the total time taken for the measurement is roughly half of the time taken in the double exposure method, because here we are not carrying out the normal incidence X-ray back reflection pinhole photography. We are using only the inclined X-ray method for the back reflection pinhole photography. Therefore, this method, single exposure method, about 50% of the time taken in the double exposure method, but the error in the single exposure method is 2 to 3 times the error that we encounter in the double exposure method. Normally, if we use a still sample by double exposure method, the amount of error is about plus minus 30 to 35 MPa for still samples. But as we can see that in the constant k values, there is always this factor E, the Young's modulus. So, naturally the error will be much less for a material which has lower Young's modulus value. Therefore, say if we take aluminum alloys, the error in the measurement of stress by the double exposure method will be much less than in case of measurement on steel samples, so to say. There is another method by which we can measure stress, and that is the diffractometer method. Now, since in a diffractometer 2 theta is measured directly, it is convenient to write the stress equation in terms of 2 theta, not in terms of d. So, if we differentiate the Bragg law, delta d by d is minus cotangent theta delta 2 theta by 2. Combining this relationship with equation 8 we can write sigma phi is equal to E cotangent theta 2 theta perpendicular minus 2 theta psi divided by 2 into 1 plus nu sin square psi. Now, you see, due to the presence of stress in the material, there will be a shift in the position of the lines, there is a change in the d values, and that will automatically lead to a shift in the 2 theta values. So, this is the 2 theta value when we do it under normal incidence of X-rays, and this is the 2 theta value which we find out under the inclined incidence condition. Now, if we put k double prime is equal to this value which can be calculated, we can write the sigma phi is equal to k double prime 2 theta perpendicular minus 2 theta psi. So, in this case, in the diffractometer method, it is simply to figure out what is the what is the shift in the value of the 2 theta angle. Now, here it is a schematic of a back reflection pinhole camera. This is the X-ray tube, focus spot of X-ray tube, this is a pinhole, this is the specimen, and this is the film. So, the back reflected rays are obtained in this manner. So, this is the schematic of a back reflection pinhole camera, and this shows the angular relationships between the specimen, the counter, the focusing circle, etc. in the two cases. Here this is for in the diffractometer. Here in the diffractometer, this is the condition for normal incidence diffractometry, and this is for the inclined incidence diffractometry. So, we can see here under normal incidence, if this is the specimen and this is the diffractometer circle, this is the focusing circle. Focusing circle is always tangent to the specimen, and this is the location of the counter. So, in the normal incidence method, the perpendicular to the specimen and perpendicular to the plane which is diffracting, it is the same. But what happens when we have the incidence, inclined incidence X-ray diffraction? There the specimen is rotated by an angle psi, as you can see here. So, the NP, the normal, and the NS, NP the normal to the plane and NS the normal to the specimen, they are quite different here. So, NS changes by an angle phi. Now, in this case, the diffracted beam gets focused at f prime, much before it reaches the counter. So, what normally is done, if in this particular case, if it is focused at f prime, then in the counter the intensity will be much less. Now, in order to avoid that, we can use a bigger slit here, but in that case the resolution will be very poor. So, the ideal case will be if we have a small slit over here and you can put the counter somewhere above there, but normally what is done, we put the slit somewhere in between f dash and f. So, that will in that method we make a compromise between the resolution and the intensity. So, this is this explains as I said how stress is measured by the diffractometer. Now, coming to a conclusion, stress measurement by X-rays is quite useful when we deal with lot of high localized stresses in a material which varies over a distance from place to place. Their X-ray method is very useful compared to the electrical or mechanical gauges. In fact, for residual stress measurement, the X-ray method is undoubtedly better than the electrical and the mechanical strain gauges.